Welcome to a lesson with Dr. Powell. We're going to look at a way of writing down, a rigorous form of writing down what a limit is. Um, this type of rigorous wording of what a limit is very useful for proofs and motivating kind of how things work and be able to make things pretty rigorous. But it also has some applications when we're dealing with tolerances and other things, and it comes up in writings and other that even engineers have to look at occasionally. So it's good to have some familiarity. It's mostly culture at this point. So let's suppose that we have a limit of a function, okay, as x approaches something like 5. Okay, so x approaches 5. So then what we do is we think, okay, we're trying to narrow in. So as x gets close to 5, we want the y values to be in the function itself to be getting close to that point as well. So what we do is we set kind of a tolerance up and down from that point. We call that epsilon. We give it a name. It's a Greek letter, epsilon, standing for error, but it really just means a kind of a distance here. I mean, we could have used anything, but let's just use a Greek letter here to represent a distance we mean above and below. Now, what we'd like to be able to do is say, so given this tolerance, does there exist, which basically is like a y closeness. So think of epsilon as kind of being like a y closeness. So given a y closeness, does there exist, so given the y closeness, does there exist an x closeness? So a closeness about this point in terms of x, such that if we're close enough, that if we're in that box of x closeness and y closeness, that the function itself will be contained within that y closeness right there. So we're not going, the y values are going to be within the y closeness. So it exists an x closeness such that if we're in it, or if the function, or such that if our x values are in it, then the y values will be in the y closeness. Now, this is kind of a technical definition of what it means if this is satisfied for any y closeness at all. So see how I said given a y closeness, so that means given any y closeness at all, whether it be big or far or small, especially small. So no matter how small we get in there, there's always a way to kind of restrict our x values so that our function is really that close to that point. I mean, it catches things like this. I mean, what if, you had something like a function that looks like this, right? And let's suppose that, in fact, that function works. Okay, so let's suppose that, I mean, if we picked a y closeness like this that was too big, then an x closeness like this, the y values are contained just fine. But what if we made it smaller and went about where the function is defined right there? And is there an x closeness such that when we're in those x values, the function defined at those x values is within the box? No, it's not. Look, it's out here. So it detects that. It's kind of like a detecting tool or idea written in a rigorous mathematical logical way, so that we can actually say if something is continuous at a point, or if a limit exists. I mean, the two are equivalent there. Does it really work? So so this is kind of the technical definition of of that, and it needs to work and hold for every single tolerance value of epsilon that we have. In the next video, we'll actually write out some inequalities that go through this idea. So we're not just saying y closest is the next closest, but we're actually using inequalities that actually mean these things. Thanks for watching.